Welcome to my channel. Today we are going to look at vector spaces and subspaces. Now, when we talk about vector spaces, we are saying that it's a set of objects with operations of vector addition and then scalar multiplication satisfying the following axioms. Thus, we are saying that it's a set of objects with operations of addition, that is vector addition, and then scalar multiplication, and then it satisfies the following axioms. So the axioms are here. We have closure, and so we check closure under addition and then scalar multiplication, commutativity, associativity, identity, and then inverses. So under closure, it says that when we have a vector, let's say two vectors from the space V, then we say u plus V should be in V. That is the closure and the addition. And then for multiplication, that one, they're saying that when we take any scalar c and multiply it by any vector from that V, it should also be in what? In V. So I take u and then I multiply it by a scalar c, then it should be in V. Commutativity, we are saying that if you take two vectors and you add, that is u plus v should be equal to v plus u. So that is for commutativity. For the under the scalar multiplication, we don't check for commutativity, so that one is out. Then for associativity, when we have three vectors, let's say u plus v plus w. Now if I choose to group it this way, it's the same as me doing another one, u plus v plus w, and then grouping it that way. So that is also another way of doing associativity. And for this one too, they are saying that if you have two scalars, so if I have two scalars, let's say c and d, then is if I multiply the scalar by the vector where I have du, I can choose to do this, or I will choose to multiply the two scalars and then multiply that by the vector. So, and that is also fine. Now, the identity, for additive identity, we are saying that 0 should belong to v in what sense? That such that when we take 0 plus any element, any vector there, it should be equal to 0 u plus 0, and that should give you the u, that should give you the vector. And then for the scalar identity, that is 1 times the vector should give you u. Now we talk about inverses. Now is if you have any vector in the space V, what we are saying is that if you take that vector plus its inverse, it should give you the identity element, which is 0. For scalar multiplication, we do not check that. And then for distributive property, we are saying that if you have a scalar and then you have two vectors, let's say u plus v, then we can distribute the scalar over the vectors. That is, we'll have cu plus cv. And then if you have two scalars, let's say c plus d, and then we multiply it by a vector, let's say u, then what we are saying is that we can distribute the vector over the scalars. That we will have cu plus du. So these are the axioms of vector spaces. For all, if for a vein or a space to be a vector space, we are saying that it should be satisfying all these conditions that we have here. All right, now we move on to subspaces. Subspaces, and when we talk about subspaces, we are saying that subspaces is a non-empty subset, of a vector space V. Now, so we are saying that if W is a non-empty subset of vector space V, then we are saying W is a subspace if it satisfies the following axioms. What we are saying is, for a vector space, every vector space, we have the a subset. If you have a subset and then that subset is not empty, and then these conditions are met. So if, for instance, if I have a set V, then I consider another set inside, set W. Now this set W here is a subspace of this vector space V if and only if one, this W here is a vector itself, and two, it is not empty. Three, it satisfies the closure property. That is, if you take any two elements, U plus V, it should be in W. And then if you take a scalar multiplication, you multiply by a scalar, it should be in W. So C times U should also be here, should stay in this one. Then we are saying that that particular space is a subspace of this V. All right. So if we are being asked to find the subspace, we are just going to select these two properties and then test them. If we test them and then they are satisfied, then we can conclude that that is the case. Now, one thing I have to add is that for every vector space, it has at least two subspaces. At least two subspaces. That is zero subspace, the zero subspace, and then the vector itself. That is the vector itself is also a subspace of itself. So what we are saying is that for um a vector space, it has two, at least two. That's if there is no subspace there, these two are there. That is zero subspace, it contains the zero subspace, and then the vector itself is also a subspace. All right, so let's take an example and see how we'll go about it and then solve them. All right, now we want to show that this particular example given to us is a vector space. We want to show that it's a vector space. I want to clear here. So it's a vector space. All right. So this is the example given to us. We want to show that it's a subspace. We want to show it's a subspace of all real valued functions. So this is a question given to us, and so we'll go through the example step by step to see how we can go about it. All right. So without wasting my time, let's start. We're saying that, so our solution. Now, to be able to prove that it's a subspace, we are saying one, it should not be empty. And as you can see, this particular set here is not an empty set, or the real value space is not an empty set. The next thing is that we are going to show the sum of two vectors should be in W. And then when we take a scalar and multiply by the vector, it should also be in W. So these are the two things we want to show. So we are going to show these two things. So you put this one in mind. Now the first thing we will do is that we will have to create two um, polynomials so that we can add them and see if really we will still get something that is in the subspace. So we say let p of x be equal to an xn plus an minus 1 xn minus 1 plus ax plus a naught. And then the second one is that we will let q of x be equal to bn xn plus bn, sorry, n minus 1 xn minus 1 plus bx plus b naught. So what we want to do is that we want to prove that the sum will be in W. So we are going to look at the sum. So we have p plus q of x should be equal to p of x plus q of x, right? So in that case, when we are adding, as we have here, when we are adding, we'll have adding. We'll have the first one. We say that p of x plus k of x. So if you are going to add, you're going to have a n plus b n x n plus a n minus 1 plus b n minus 1. That will be all x n minus 1 plus a plus b x plus a naught plus b naught. Right. Now, if you look at this and you compare it to the equation star given to us in the question, you can see that they look similar. So we can say that since p plus q of x, right, looks similar as equation star, then we are saying that since it looks like equation star, then p of x plus q of x lies in w. So that is the first one. Now we will prove scalar multiplication. So also for any scalar, and then the scalar we are choosing c for any scalar, then we'll have c of p of x. So we have this to be equal to c of p of x, right? So if I multiply the p by c, what am I going to have? I'm going to have c a n x n plus a n minus 1 times c. That will be, so we have the c here. So we have c a n minus 1 x n minus 1 plus c a x plus c a naught. So now we can see that this one also looks like the original equation given to us, that is the equation star. So since it looks like that, we can also say that since cp of x looks like equation star, then we can say that cp of x lies in w. Hence w is a subspace of Venn. Alright, so what have we discussed in this video so far? We've discussed that a vector space is a space that satisfies these axioms. It should be closed under addition, multiplication, scalar multiplication. It should be associative, and then we should have an identity that is for both scalar multiplication and then the addition, where we have addition to be 0, the identity to be 0, and then for scalar multiplication to be 1. And then we are also saying that it should be distributive. If you have two scalars, you can distribute. So all these conditions, if they are met, then we are saying that it's a vector space. Similarly, we will talk about subspaces. That is, when we consider a vector space, we can take subsets of from the vector space. But for you to be able to call that subset a subspace of that vector space, we say that it is satisfy to three conditions. The first condition is that the set you are choosing should not be empty. Secondly, we are saying that the set should be closed under addition, and then it should be closed under scalar multiplication. If these conditions are met, then it's a subspace. Thank you for watching, and then share, like, and then subscribe to my channel so that we can grow together. Thank you.